Okay, good afternoon / evening, everyone. Welcome to the ALCF AI for Science training program. My name is Junie Ramprakash. This is our third session, and today Asad Khan will be presenting an introduction to deep learning. As in previous sessions, all questions and comments will be handled through Slack. Please join the channel for today's lesson called O2 Deep Learning, if you haven't already done so. And you can visit the general Slack channel and use the link provided there to join today's lesson channel if you need it. So without further ado, I'm going to hand it over to our speaker for today, Asad. Thanks.
Yeah, thanks, Ginny. So can everyone hear me fine? Okay, great. Well, thanks. So yeah, my name is Asad Khan, and I'm a PhD student in physics at the University of Illinois, Urbana-Champaign. And I'm also a visiting student at Argonne National Lab. So glad to be here. So before we get started, I would just like to point everyone to the GitHub repository for this tutorial. If you have been coming to the previous two tutorials, you already know where that is, but in case you don't know, please go to this URL. So on my screen right now, I'm showing the repository. And then within the repository, please go to 02 Deep Learning folder. So once you're there, I have listed some of the instructions to get started over here. And in case you don't have this repository on your ALCF system, make sure to log in to Theta. So you need to spin up a terminal on your own computer, SSH to the Theta machine. So you'll have to replace username by your own username and enter your password. And then make sure to clone this repository. In case you have already cloned the repository, you just need to make sure to pull it once again so you have the latest material. So that would just be git pull, the command. So presuming everyone has the repository on Theta, then what we need to do to go through these notebooks is first spin up Jupyter Lab session. So the instructions for that are similar to the last session. I've listed them again here in case anyone needs them. So please click on the first hyperlink, which says login to Theta GPU, compute node via Jupyter Hub. So if we go there, I'm just going to go through these steps with you. Then on top of the document, it lists this link. So we'll need to click that. And then you would need to log in once again to Theta GPU. So make sure you have three options here, GUI, Theta, and Theta GPU. Make sure you pick Theta GPU. So once you click that, I think it will ask for your password once again. If you're already logged in, you will see a page something like this. That would look something like this. So from here, we just once again need to pick Theta GPU compute node. Then we need to pick the appropriate queue. So please make sure to pick a single GPU. And then you need to list the project. So for most of you, unless you're already on the system, you'd only see ALCF AITP as one of the projects listed. Please make sure to pick that. And here you need to put, I think this session will run for 2 hours, so maybe 120 minutes. And then you click start. All right, so it looks like I'm in. I'll still wait perhaps a couple more minutes for other people to get here as well, because I still see some people posting they're getting errors. But while we wait, let me just once again remind everyone that you're supposed to git clone the repository. So if you have, then you should see a folder saying AI Science Training Series. And once again, if you have already cloned this repository, meaning you had cloned it a week or two ago, then you need to make sure to update it. And you do that by running git pull command. the terminal. So just make sure that you have the latest commits pulled into the repository. And then for this week, we are going to go through material in this folder, 02 Deep Learning. So within this folder, you should be able to see 3 notebooks, Intro, MNIST, and C410. And we're going to go through these notebooks in this order. Okay, if I see a comment that when they log into Jupyter, they're not seeing the drop-down menu, but seeing the AI training series landing page. I mean, if you're seeing this, then you might have a session already running. In that case, you're good. Only in that case, if you run out of time, you'll just have to go through the steps again. So if anyone is having any difficulties logging in, please post it in the chat right now, and I'll wait another minute. Otherwise, we'll just get started.
Asad, you might want to zoom in a little bit and mute your Slack notification audio.
Oh yeah, that's... Sorry, let me zoom in first. Is this good?
Yeah, I think that's better.
Okay. And can someone tell me how to mute Slack? I'm not very used to it.
You could just quit it for now. We'll handle all the questions.
Oh, okay. All right, so we are 15 minutes in. Let's get started. If you're still having trouble, please post it in Slack and somebody would help you get started. But also, I already have the outputs in all of the notebooks already printed. So you don't really need to run them. You can if you want, but you can also just go through the notebook for now, or look at my screen for now. And once all the issues are resolved, then you can run those notebooks on your own time. So the first notebook, Intro, the motivation, well, let me just say the motivation behind the whole tutorial is to give introduction to people who have had very little exposure to deep learning. So you might have heard about the term and might have seen some concepts, but never had a deep dive into it. So the idea here is, in the first notebook, we're just going to touch in a bare minimum way some of the theoretical concepts. And then starting from the second notebook, we'll quickly build up on those concepts and start coding very quickly to solve some toy problems, to give a more hands-on approach to the topic. So when introducing deep learning, I thought people usually hear the term deep neural networks, and I thought maybe a good point to start would be to look at a single neuron in a deep neural network, because these networks are made up of a bunch of neurons. So what does even a neuron mean? Now, historically, these mathematical neurons were motivated by biological neurons. So I thought maybe let's delve into that analogy for a little bit. So here, what I'm showing on the left-hand side is a biological neuron. It has a bunch of dendrites, which take incoming signals. Then there's a nucleus or cell body, which you can think of doing as some kind of computation. And then there is an axon through which outputs go and then connect with other neurons. So what's the nature of the input signals in a biological neuron? The input signals come in as pulses of electrical pulses with certain frequency. And if the frequency of the incoming signal passes a certain threshold, then there is an outgoing signal, which goes on and connects with other neurons. So structurally, if we draw this mathematical neuron in a deep neural network, it kind of looks very similar to a biological neuron. What we have here is a bunch of inputs coming in, and this circle represents a neuron. Then some kind of computation goes in inside that cell, and then we apply some kind of threshold on that computation. So if the value is above the threshold, then there will be an output. Otherwise, there'll be no output. So we'll just output a 0, perhaps. So that's basically the structure of a mathematical neuron. Now, the question is, what kind of computation goes inside the cell body? And is that also really motivated by biological neurons? Well, at that point, I'll just, I don't really know, so I'll just leave this analogy there, but I'll describe to you what happens inside the cell body. So last week, you were already introduced to linear regression. And turns out what's happening here is also just a single dimensional linear regression, okay? So an input comes in, and then you multiply it with some weight, add some bias, and that gives you your output, okay? So this is basically the equation of a straight line, right? So y equals mx plus b, which we are familiar with. And then the output, to the output y, we sometimes apply some nonlinear function, and that defines our outgoing signal from the neuron, okay? So when we're talking about a deep neural network, what's happening inside each of these neurons is linear regression. So it's a bunch of linear regressors connected in an acyclic graph. And we stack these layers together, and that defines basically a deep neural network. So I know you have gone through linear regression last week, but let's just do that once again to give a quick refresh. So we know that to fit to a straight line, we actually need just 2 points, right? Give me a set of 2 tuples, y and x values, and then I can fit and find the equation of the straight line. But in data science, the problem is we might have reason to believe that the data lies on a straight line, but we collect it and there could be some noise on top of it, right? And so in the presence of noise, then 2 points wouldn't be enough. You really need to gather a bunch of data and then find the best fit line. And that's the idea of linear regression. So let's simulate that. What we do here is, let's first define the underlying theoretical line, y equals 2x, and then on top of it, we add some random noise. And once we do that, then our data looks like this. And now the problem for us is to actually find the underlying equation of line and defining this data. Let's run this. Okay, so last week, I think you went through this problem and you know that this can be solved exactly because this is a convex problem. So there is a global minimum. And so you can find that global minimum exactly. But another way of doing this is actually through gradient descent. And the idea there is we can start with some random guesses for the values of m and b. And with that guess, we can find the predicted values, right? Denoted here by y tilde for all of our input values, right? So that's basically saying you can start with a guess line and then find the error between or the distance between all these points and your guess line, right? Whatever your hypothesis line is. So you find the distance through mean square error. We find the distance between your guesses and the ground truth values and square them and divide by the number of data points you have. So that's our error function here. And what we do now is, instead of trying to solve it exactly, what we can do is find the gradient of your error function with respect to the variables that you're trying to find. So M and B here. And if you remember from Calculus 101, the gradient gives the direction of steepest ascent. So if we take a step in the opposite direction, then we'll start moving towards the minimum of the loss function. So that's basically what we do in gradient descent, except we attenuate how big of a step we take by this parameter alpha, which is sometimes also called the learning rate. And you have to be careful about picking this alpha parameter, because if you pick too small of a value, then it will take forever to go to the minimum. But on the other hand, if you take too big of a step, then your loss will start diverging actually. So there is a fine balance that you have to pick. And in a later notebook, perhaps we'll talk about how to find an optimal alpha value. Okay, so to find the gradient, well, in this case, it's very simple. We all know how to compute it mathematically. This is the formula for the derivative of L with respect to M and of L with respect to B. So we can find these values exactly. And that's, in a sense, the essential machinery behind these deep neural networks. Okay, so we don't approximate the gradients, but we find them exactly. Meaning we find mathematically what the gradients should be at this point. And then we compute the X and Y values and our predicted values to find numerically what those are. Okay, so this is simple enough that we can write it out ourselves, this whole procedure. So let's do that. And so step number 1 is coming up with guesses for M and B values. So we just do that here, we'll pick some random values. And let's plot that line. So let's say this is our first guess. And now let's write down this whole gradient descent procedure in code here. So we have to pick, define our learning rate, alpha. So we have to be careful about picking this, not too small, but not too big as well. And then epochs basically defines how many times we want to repeat the step. Okay, so each time we find the derivatives and take a small step in the opposite direction and update our parameters like so, right? So how many times do we want to repeat this procedure is called the number of epochs. So let's say a priori, we just decide that we're going to do this 10,000 times. Now, once again, this number has to be picked carefully. You don't want to stop too early, but you also don't want to run it forever, right? So once it reaches the minimum, perhaps you have to carefully look at the loss, how it's decreasing. And once it stops decreasing appreciably, then perhaps you need to stop. Okay, so then comes the for loop. We repeat this gradient descent steps 10,000 times. So each time what we do, we first compute our predicted values. So right now we have guesses for M and B. We go through our data and compute the predicted values. Then based on those predicted values and the ground truth values, we compute the loss, which is the mean square error in our case. Next, we compute the derivatives of the loss with respect to M and B. So those are given here. And then we update our parameters, M and B, by taking small steps in the opposite direction. So we subtract these derivatives. And so what we're doing is every 1,000 epoch, we are also just going to print the loss to see what's happening. So if we run this, we should see that the loss is decreasing. Now it looks like we could have kept it running for a while longer, because this is still decreasing. So you can play with this number of epochs here and find out how many epochs you actually need for the problem to converge. But let's just look at what the line looks like after 10,000 epochs. So it's already looking pretty good, right? And so instead of exactly solving this problem, this loss function to find the global minimum, we actually use this machinery of gradient descent. And why do we do this? Is because when we go to deeper neural networks, this becomes essential. Because so far for this simple linear regression problem, we have a convex optimization problem. We just have one global minimum, which we can find mathematically exactly. But once you stack a bunch of neurons together in a number of layers, then your loss might not have a one global minimum. And so this this won't be a convex optimization problem any longer. And so you won't be able to find exactly the minimum. And so in that case, our machine, like the only way to find some local minimum would be through gradient descent. Okay, so that's basically what's happening inside a single neuron in a deep neural network. So each neuron is a linear aggressor, and each one is updating its parameters through gradient descent. Okay, and what is this output value that it's trying to fit to? Well, that's something we don't know right now. Okay, so if this was a single neuron and we were trying to fit to a straight line, then of course it's very interpretable. We are trying to basically find the best fit line here, and we're perhaps trying to model some phenomenon. But when we have a bunch of neurons, each one is trying to fit to something which could be abstract and not very easily interpretable. But we'll discuss that later on. Okay, so first question then becomes, how do we go from single neuron to many neurons, and then from one layer to many layers, right? So going from single neuron to multiple neurons is basically dictated by the dimensions of your problem space, okay? So up here, we just had a straight line, one-dimensional. We had one input and one output. But let's say if we had multiple inputs and multiple outputs, then we would have a system of equations that we would have to solve. And so we can write those system of equations in matrix form as well. So our parameters become a matrix. This M value becomes a matrix, W, and B here, instead of being a number, becomes a vector, right? And so now this is a matrix equation, and we're trying to solve that, okay? So the shape of this matrix is, of course, dictated by the input space dimension and the output space dimension. So if you're going from 4 dimensions to 3 dimensions, then of course, this matrix would be 3 by 4, right? So when people draw out these neural networks, essentially what they're showing is this matrix multiplication, right? So let's say our input space is 3-dimensional, and let's say our output space is 4-dimensional. Then this matrix multiplication can be visually shown like this, okay? So all these arrows are pointing to this matrix multiplication. So for example, this neuron here would perhaps correspond to this output here. And how do we get this output? Well, we take the first row of the matrix and multiply by all of the inputs, then add this first value of the bias vector, and that gives us the output. And here what's happening, we're taking all of the inputs, we're multiplying by some value, which is shown by the strength of this line. So this row is represented as a line here. Each value of the row is represented as a line. So we're multiplying the input by that value, and then adding them up together, adding the bias value, and that gives us the output. Of course, we're not showing this addition here, but that's basically what this visual representation means. This is basically matrix multiplication and then adding a vector. Okay, so that then now we know, okay, the dimensions of our input and output spaces dictate the dimensions of the matrix. But how about these deep neural networks, which generally means having hundreds of layers? So how do we get that?
There's a question.
Yes.
In chat, since you don't have it open anymore,
Sure.
asking, shouldn't the output layer have 3 circles?
Yeah, sorry about this. Like this up here doesn't correspond to this picture here. Also because here we have, in a sense, 2 layers, and up here I'm just showing 1 matrix multiplication. So sorry, there is a mismatch. They're not supposed to correspond to each other. But this would correspond to going from 3-dimensional space to 4-dimensional space, and then again from 4 to 2-dimensional space. So essentially what we're doing here is two matrix multiplications, right? And that essentially takes us to multiple layers as well, what I was going to talk about. So the idea is up here, we had our inputs, and then we just did 1 set of multiplications, and we got our outputs. But on a more conceptual level, like there's nothing stopping us from repeating this operation a number of times. Okay, so instead of just applying one set of matrix multiplications to the input and then calling that our output, we can in fact repeat this operation once again, right? And then whatever we get, call that our output. So in theory, we can do this any number of times, right? So then whatever intermediate results we get become some kind of latent space, okay? So we are first transforming our inputs to some latent space, and then going from one latent space perhaps to another latent space, and so on. And we can repeat this any number of times until we decide that we're going to stop there, call this our output. Okay, so that's what we're doing down here. We first do some matrix multiplication, go to some latent space, another set of matrix multiplication, another latent space, and then final set of matrix multiplications to get our output. So conceptually, nothing is stopping us. And the reason people do this is because turns out in deep learning, you're trying to learn in a hierarchical fashion. So instead of doing these matrix multiplications once, if you do it a number of times, it gives you more representational power, okay? And we will empirically see this in the next notebook when we actually solve a problem. But some of you might have caught on to something here, and you might already be wondering, like, what I said doesn't really make sense, because if we apply a bunch of matrices, in the end, we get a single matrix, right? So what does that even mean, getting more representational power? We're just basically composing a bunch of linear maps, and well, instead of a bunch of linear maps, I can just call that one linear map, and it's the same thing. So all these layers just collapse back into one layer once again. And that's where this fundamental idea of, or essential idea of nonlinear function comes in. So we talked about this, but we didn't really apply it in this toy problem. But in reality, when we deal with deep neural networks, each neuron will do this linear regression problem, but then afterwards, it will apply some nonlinear function. So once you apply this nonlinear function, then it is no longer a composition of linear maps. You actually get a nonlinear mapping from input to output space. And that's where this whole representational power of deep learning comes in. So I would say that's basically it. Those are the building blocks or essential concepts involved in deep learning. It's basically very simple as long as you have some background in some of the basic maths, basically. So as long as you have some exposure to some basic calculus and linear algebra, then those are all the concepts involved in deep learning. So just to recap, for any given problem, of course, we have to define a loss function. So we have to be able to judge how good our model is doing. And so for that, depending on the nature of the problem, we'll define a loss function. So in this case, we were doing regression. Therefore, we picked mean square error. We could have also picked mean absolute error. But if we were doing classification, then we would perhaps pick cross entropy. I know you guys talked about, I think you guys talked about that last week. So instead of, if we were doing linear regression, if we were doing logistic regression, then we would use cross entropy loss. So the loss is kind of dictated by the nature of your problem. And then how do we find the parameters of this deep neural network? It's through gradient descent. So we first start with some random guesses for all the parameters. and then find the hypothesis for those random guesses, compare it with the ground truth, compute the loss, compute the gradients, and then update the parameters based on the gradient. And then there is this term called backpropagation that you might have heard of, or you would come across a lot in deep learning. And what does that mean? So backpropagation is basically chain rule from Calculus 101. Okay. So when we had a single layer up here, it was pretty straightforward to compute the derivatives and then update the parameters. But once we have like a number of layers, then the deep neural network could be written something like this. So our x is the input here. We multiply it by some matrix, apply some nonlinear function, another matrix, another nonlinear function, until we get our output. And now the question is, okay, I have my output, I compute my loss. How do I find the derivative of the loss with respect to all of these parameters? And well, Calculus 101 tells us that we have to apply the chain rule, right? So to do that, we first compute the loss with respect to fn, then with respect to wn, and so on. And visually, this sort of looks like propagating the gradients backwards. So if we call this forward, giving the input and then computing these matrix multiplication and nonlinear function and so on until we get our output, we call this the forward pass. Then doing gradient descent sort of looks like propagating the gradients backwards, and that's why I think it's called backpropagation algorithm. And then right now we are using just Python to write out the derivatives, but the power of deep learning APIs, which we will dive into in the next notebook, comes in automatically creating these computational graphs, which keep track of the gradients. So we don't have to write out all these derivatives by ourselves. So it takes care of the backpropagation algorithm for you. And we'll work with one of those APIs in the next notebook. And then optimizer is basically what I would say right now, different flavors of gradient descent. Okay. So for now, let's just call these different flavors and stop there. But in the next notebook, we'll dive into a little more detail about what optimizers are. And then activation functions, of course, are some kind of nonlinear function. So far, we have no example of it right now. But in the next notebook, we will work with a few examples of these activation functions. Okay, so next, I'm going to go into convolutional neural networks. But let me take a pause here and see if there are any questions so far. All right, if not, then let's go to convolutional neural networks, are also called CNNs. And this whole resurgence of deep learning in 2012, I think, started with a particular type of neural networks, which were CNNs. So there is a famous image competition called ImageNet. And for a long time, it was a really hard problem. And then in 2012, the winning solution used CNNs, and there was a big jump in terms of performance. And that sort of restarted this interest in deep learning. So a lot of these ideas go back into the last century. And for a long time, they were there, but a lot of people weren't really working with them. And then with this ImageNet competition in 2012, there was a resurgence of interest because of CNNs working very well on image datasets. So what is CNN? So far, let me just say, so far what we have worked with is fully connected neural networks. These are called fully connected neural networks. And then now we're going to talk about convolutional neural networks. So convolutional neural networks are also, some people, I think people say they're also motivated by the structure of visual cortex in the brain. I'm not really sure about that, but I do know that these convolutional filters have had a long history themselves. So what people used to do in the past is try to design interesting filters and then apply them to the pictures, to images, in order to pick up some interesting features. Okay. So how would they do that? Well, what you do is you start with a small filter, let's say 3 by 3, and you define some values in the filter. For now, let's consider them fixed. And then you apply them on different patches of an image to get an output. And so what does this convolution operation mean? It's basically a dot product between your filter and a patch of your image. So for example, if you apply this filter to this patch, we're basically doing a dot product. So we're multiplying 1 times 1, then 0 times 0, and 1 times 0, and then adding those all together, and that gives us a single number output. And so what we do is we start with on the top right corner and then slide it to right, and then we go down, slide left to right, and so on until we have swept through the entire image. So once we do that, then we get an output image, or we can also call it an output matrix. And so the idea here is, in images, there is some kind of position invariance involved, right? So let's say if we were trying to classify images of cats and dogs, whether the cat is in the top left corner or the bottom right corner shouldn't really matter. So it doesn't really make sense to have fully connected layers because those are not translation invariant, right? So once you, for example, here, once you train this network, if you shift your input up or down, this network will stop working, right? Because each weight here is specialized to look at a certain input. But in images, naturally, it makes sense to have this translation invariance, or perhaps even rotational invariance. So what these filters do is, by sliding them across the picture, we incorporate that translation invariance, right? So each filter will now be specialized to pick up a certain feature, no matter where it is in the image. And so back in the day, people used to hand design these filters. And let me give you a few examples of those. So if we start with a sample image here, and then if we define the convolution operation, basically what I described up here, just code it down here. So we're just sliding left to right and up to down. And then we can pick some interesting filters and apply them to an image, right? So for example, there is a vertical edge detector. If you fix the values of the filter to these, and then apply this to an image, then what you would get is, what would happen is that this filter would pick up vertical edges in the image. And same thing, similarly, there is a horizontal edge detector. And hopefully we'll see horizontal edges getting picked up. And likewise, perhaps there is a filter that sharpens the image and so on. So previously what people used to do is they used to spend a lot of effort coming up with interesting filters so that they can pick up interesting features. And then based on those features, we can perhaps classify what's in an image. With deep learning, the idea is somewhat flipped once again. So instead of coming up with these values, what we do once again is randomly initialize the filters and then learn these values through gradient descent. Okay. So similarly to linear regression up here, where we randomly initialize the M and B values and then let gradient descent learn those values, we do the exact same thing here. We randomly initialize the values of the filter and then learn it. Okay, so now that we know what a convolution operation is, then a complete convolutional neural network looks something like this. So we'll start with an input image. We'd apply a bunch of convolutional filters. And that would give us some output. Then we apply something called max pooling. And what that is once again very similar to applying a filter, but what we do here is we just pick the max value in the patch, right? So let's say we apply a 4x4 filter. So in this 4x4 patch, the maximum is 20. So we just pick that. Then we go to the next 4x4 patch, pick the maximum value, and so on. And this is just an efficient way of spatially decreasing the size of your tensors here, or matrices. Okay. So on a higher level, that's all there is involved. You apply a convolutional layer, max pooling, another convolutional layer, max pooling, and so on. And then at some point you decide, okay, we have applied enough number of convolution operations, enough convolutional layers. So let's flatten this out. And then usually what you do is afterwards you apply a bunch of fully connected layers, and then you get your output, okay? So let's say if you were classifying images of cats and dogs, we first apply a bunch of convolution operations, then we flatten it, apply a fully connected neural network, and then the last layer would give us perhaps a probability whether the image was of a cat or a dog. So let me say a few more words about max pooling. Why do we do this? And for that, let me actually first go up here. So one thing you would notice is after we apply the convolutional operation, the output matrix is of course already slightly smaller in size, right? So the exact relationship between the input dimensions and the output dimensions is given here. So let's say if our image was of width W and height H, and we apply a filter, n by n filter, then the output size would be this. And so here, I'm also listing a couple more hyperparameters, which we didn't discuss, which is padding and stride. So stride, of course, means by what amount we slide the filter from left to right and top to bottom, right? So we can just go one step to the right, one step to the bottom, and so on, and that would be stride 1, or we can like skip some pixels in between. And then padding is the concept of padding comes in when you don't want the output to be of a smaller size. Okay, so perhaps let's say we want the output to be of the same dimensions as the input. Then one way to achieve this is if we pad the borders of the image with zeros. So in this way, we artificially increase the size of our input image. And now when we apply the filter, the size decreases, but the output ends up matching the dimensions of our input image. So in case we apply padding, then this is the relationship between output and input. And so we also, so it's not just simply that you would want to match the input and output dimensions, but also if you closely look at this operation, you would notice that the pixels in the center of the image get twisted by the filter a lot more than those in the edges. And this, in some applications, could be undesirable, right? Perhaps you want to give equal weighting to all of the pixels. So that's also a situation where you would apply padding. Okay, anyway, so whether you apply padding or not, what you would see is that the size either doesn't decrease or decrease slightly. But when we apply hundreds of layers of these convolutions, the computation still is sort of very intensive, right? So we want some way to decrease this computational intensiveness. And one way to do that is to apply max pooling. And so in max pooling, what you're doing is picking up the most salient features in these 4x4 patches. And so this way you reduce the dimensions without losing too much information. So in practice, it works out very well. You end up decreasing the computation by a lot, and at the same time, not losing a lot of information. Okay, so I think that's basically it. I think we should be equipped with these concepts to actually go and start building neural networks and start solving some toy problems. So before we go to the next notebook, once again, let me take a small pause and make sure if there are any questions. Yes, please go ahead. I see a hand raised.
I have a question about rotational versus translational invariance. I'm not really sure what that means.
Sorry, up here when I mentioned the image. So the convolution filter helps with translation invariance.
Yes, I don't quite follow.
Oh, okay. So let's say this filter is specialized to pick up vertical edges, right? So then translation invariance basically means no matter where that vertical edge is in the picture, this filter will still pick it up. And the way it does it is simply because we are sliding it across the image, right? So if the vertical edge is up here, then when we apply this filter to this top right patch, top left patch, it will pick it up. And if it's down here, then once we apply it down here, it will still pick it up. So regardless of the location of this vertical line, if the filter learns to pick up vertical edges, then it will. Does that make sense? Or on a higher level, if this filter was designed to, let's say, detect cats, then no matter where the cat is in the image, it will still detect it. So that's what translation invariance means.
Thanks. What about rotational invariance?
Okay, so rotational, by default, this filter will not be able to deal with rotational invariance, but we will talk about how to include that. So actually, let me just say it now. The way you do this is during training time, if our problem allows, then we can introduce some random rotations of the image during training so that the filter sees different rotational realizations of the same object, right? So for example, a cat and dog problem is one where there is rotational invariance allowed. So an upside down cat is still a cat. So what we would do is randomly rotate pictures of cats, and we are asking this filter to learn to detect cats. And as long as it's seeing all the different rotational realizations of the cat, it will still learn how to detect it. But some problems might not allow that, right? So if you're classifying digits, if we rotate 9, it will become a 6. So we can't have that. So some problems would allow rotational invariance, others won't.
Thanks.
Yeah, no problem. Any other questions? Okay, if not, then let's go to the second notebook, and hopefully this would be slightly more fun because we're actually going to start building these neural networks. And hopefully you will see that how easy it is to actually do that. So I'll also ask you to either close the first notebook or shut down the kernel on the first notebook. Okay, so in this notebook, we are actually going to build up a small convolutional neural network and train it on a toy dataset called MNIST. And what MNIST is a dataset of handwritten digits. So it's pictures of handwritten digits, and the labels of the image correspond to the digit in the image. And we're going to train a neural network to classify those images accurately, right? So this dataset also has an interesting history. I think this problem was already solved in the 90s and is one of the reasons why USPS is so cheap, because with these neural networks, the zip codes can be read automatically by computers, and that reduced the cost of mailing a lot. So even though this is a very simple problem and was already solved in the 90s, I think you can solve this with fully connected neural networks. We'll still use it, and it's pretty standard to use it as an example, or even for debugging whenever you're designing neural networks. So that's the data set. And then in the last notebook, I talked about deep learning APIs. The big power of these APIs is that they automatically create computational graphs for you. So once you write these computations out, it will keep track of them and automatically compute the gradients at each of the steps. So you don't have to write out the for loop that we wrote in the last notebook and compute the gradients by hand, which can get really complex as you increase the number of layers and neurons. And so for the deep learning APIs, there's a bunch of choices, and people tend to have their favorites. Two of the most popular ones are PyTorch and TensorFlow. And within TensorFlow, then there is a kind of sub API called Keras. And so for this tutorial, I decided to pick up TensorFlow Keras. And the reason is that in Keras, there is very little boilerplate. It's sort of similar to going from C to Python, right? So again, fundamentally, if you know one API, then you can always switch to another API, just like any programming language, right? But Keras tends to be easy to start with because the code tends to be very simple in the beginning. But once you get to more advanced applications, then people tend to have their favorites. I personally use both PyTorch and TensorFlow. I don't find that many differences. Like a couple of years ago, they were very different, but now all the APIs are kind of converging to same principles. So it should be pretty easy to switch. Anyway, with that being said, let's load these libraries. So for now, just ignore this. I'm setting CUDA visible device equals 0. We'll talk about this later. But in the next cell, we are importing TensorFlow. And then from within TensorFlow, we're importing Keras. So let's import the libraries. And then on Theta, the thing is, from compute nodes, we can't communicate with external websites. So we have to set up these proxies in order to be able to download some data sets. Okay, so make sure to run this. Next, Keras actually comes pre-installed with a bunch of toy data sets. So MNIST is one of those. So all you have to do is from tensorflow.keras.datasets, you have to import MNIST. And this data set already comes divided into two subsets, the training set and the test set. And we'll talk a little more about the motivation behind splitting the data set like that later on. But in the training set, you should have about 60,000 images. Each of the image is 28 by 28 pixels. And these are black and white images, so there's only one channel. If these were color images, then you would have 3 channels, red, green, and blue. Similarly, in the test set, we have 10,000 images. These are 28 by 28 and have 1 channel. And then corresponding to each image, there is a label. So the label tells you what digit is in the image. And you would notice that I'm calling this toCategorical function on the labels. And what that does is basically converts the labels to these vector forms. So the labels, of course, are 0, 1, 2, 3, and so on up to 9. But we convert these numbers to these one-hot encoded vectors. So 0 would be a 10-dimensional vector with 1 in the 0th index, and the rest of it would be zeros. Similarly, 1 would get transformed into this vector. 2 would get transformed into this vector, and 9 would have 1 in the last index and zeros everywhere else. And you might be wondering, why do we do this? So recall in the last notebook, convolutional neural network looks something like this. So we input our image here by a bunch of convolutions, fully connected layers, and in the end, we'll get an output which will be a layer something like this. So our output will be a vector, right? And we'll design this network so that the output layer would have 10 neurons. So our output will be a 10-dimensional vector. And each neuron will be giving us the probability that the input image corresponds to a certain digit, right? So for example, the first neuron, the 0th neuron here, give us the probability that the image was of the digit 0. The first neuron will give us the probability that the image was of digit 1, and so on. So how do we compare these probabilities with the ground truth values? We can directly compare this vector to these numbers. And that's essentially why we convert the numbers to vectors, and now it becomes natural to compare these two vectors, right? So we really, when the image is of digit 0, we want this output vector to just have 1 in the 0th index and 0 everywhere else. It should be 100% confident that this was 0. So that's the motivation behind to categorical. And one more thing to point out here is that I'm dividing by 255. So you might already know that pixel values are in the range 0 to 255. And we divide by 255 to force the pixel values to lie between 0 and 1 then. And this is a very standard thing to do. Usually when you're training neural networks, you would want your input data to lie in -1 to 1 range. Okay. You can read up on that. Why do we do that? In some cases, it's because if the input values are not in -1 to 1 range, then it can lead to a problem of exploding or vanishing gradients or something like that. But I'll leave that as an exercise to read up more on why standardization is important. But even from classical machine learning, you know that standardization is important in case different features lie in drastically different ranges. So you want to bring them all together in the same range. Okay, so those two steps are important. Always make sure to normalize your data and then convert your labels to a form that makes sense and that you can compare with the output of your network. So let's look at what this data set looks like. Oops, I didn't run it. Okay. So you see these are handwritten digits, images of handwritten digits, and then the label corresponds to the digit. So this 5, 0, 4, and so on. And what does our neural network see? Well, let's pick one of the images and superimpose the values of the pixel. Then we see that the pixel values lie between 0 and 1. Zeros correspond to black, and the closer the pixel values to 1, the brighter the pixel will be. So this will be the input to our network, neural network, and then the output would be a vector, 10-dimensional vector. Okay, so then how do we define neural networks in Keras? It's very simple. A lot of the layers that we have discussed already come pre-implemented in Keras. So all you have to do is just define a few hyperparameters and then just call those layers. And then we can stack those layers together into a model. So that's what we're doing here. First, import layers, and then import models. And then we can start building models very easily by calling model.sequential. So this is how you instantiate your model, call models.sequential. Now we have an instance of a model, and now we can start adding layers to it sequentially, right? So we can call model.add, and then we define what layer are we adding. So this is going to be our first layer, which is a 2D convolutional layer, right? So actually, if you run Shift Tab on this, it will bring out this dialog window, which tells you what all these numbers mean. So convolutional layer will have a bunch of options. First of all, you have to define how many filters you want in the layer, right? So previously we just showed visualizations for one filter. You can stack any number of filters in a layer, and each one will specialize to learn something different. So we want 32 filters in the first layer. Then what size of the filter, right? We also have to specify that. So we want 3 by 3 filters, 32 of them. And then remember, in deep neural networks, after every layer, we apply a nonlinear function, which is called activation here. So after we apply the convolutional layer, what nonlinear function we want to apply, we can specify that by some activation function. So here we're using ReLU, and down below I'll show you what it looks like. And then for the very first layer, you also have to specify what's the dimension of your input. So we know our inputs are 28 by 28 black and white images. So we just specify that. We really just need to do this for the first layer, because then Keras keeps track of these shapes automatically. So for the next layer, it will automatically calculate what would be the shape of the output from this layer. And so then correspondingly, what should be the input shape for this layer. So once we fix this, the rest are automatic. So after the convolutional layer, then we apply max pooling. Again, we have to specify the size of the patch. And we should apply max pooling on 2 by 2 patches. Then another convolutional layer, another max pooling, and then one more convolution. And so at this point, we can see what does our model look like. So you can call this model.summary method, and it will print out the summary so far. So we start by 28 by 28 black and white images. Once we apply a convolutional layer, the output size decreases slightly because we're not applying any padding here, right? So it goes from 28 by 28 to 26 by 26. And since we applied 32 filters, now we have 32 channels. Then we apply max pooling. So that basically halves the spatial dimensions from 26 by 26 to 13 by 13. And we still have 32 channels. Then another convolutional layer. Again, the spatial dimensions decreased slightly, but this time we had 64 filters. So the number of channels increased to 64, another max pooling, and another convolution. And then it also prints out a summary of how many parameters you have and how many of those are trainable. So in our case, all of these parameters are trainable, and we have 55,744 of them. Okay, so I said after a certain point, we flatten out the output and then apply a fully connected neural network. So let's do that. Perhaps this is a sufficient number of convolutional and max pooling layers. So then we can do that very simply. There's also a layer called flatten. So we can call layers.flatten and add that to the model. And then fully connected layers are called dense in Keras. So we can say layers.dense, and then how many neurons should this fully connected layer have? So let's say 64. And again, we apply ReLU activation after the layer. And then for the last layer, since we have 10 digits and we want each neuron to give the probability for one of the digits, then it makes sense to have 10 neurons in the last layer. And here we are applying a special kind of activation function called softmax. So if you remember from last week's tutorial, if you're doing logistic regression, you apply a function called sigmoid. And so in logistic regression, you have two classes, right? A positive and a negative class. But if you have more than two classes, then the generalization of sigmoid, you can think of softmax as a generalization of sigmoid, okay? So this will give the probability of, in case you have more than two classes. So it will give you the probability for each of the classes. And I'll show you mathematically what it looks like in a bit. Okay, so that basically describes the whole network. So let's run that, and now model.summary should print out the whole network. So we have a convolutional layer, max pooling, we have already described this. Then after this layer, we flatten out this matrix into a long vector of dimension 576. Then we apply a fully connected layer with 64 neurons, and then a final layer with 10 neurons. So that's basically our network. Any questions so far? Okay, so this is actually an extra point to take some questions because we also need to restart our notebooks. So if your tutor lab timed out, please once again go back and start a new session. So
I would recommend, can I interrupt here for a second? Sorry, the way the reservations are working for this session is I recommend requesting 30 minutes right now. Otherwise, you might be stuck waiting a long time because everything's going to switch over after 5.
Okay. Okay, yeah, so please make sure to ask for 30 minutes this time. So once again, please pick single GPU, ALCF AI project, and then I think it's by default 30 minutes. If not, please make sure that this is 30 minutes. Okay, so while we're waiting for that to run, perhaps we can at the same time also progress here. Okay, so far we have defined the network architecture, but there are still a couple more things we need to define, right? So we need to define our loss function, which we haven't so far. And we also have to specify an optimizer, which in the last notebook I said was a different flavor of gradient descent. So it's important, it's compulsory in Keras to pick one of those flavors and say, I'm going to use this flavor and define a loss. And then additionally, we can also track a bunch of other metrics if you want. So to do that, what you do is you call the compile method on the model. So we have defined the architecture of the model, and now we can call model.compile. So first, you can give it the optimizer. We are going to use this RMS prop version, and you still have to define the learning rate, which is the alpha parameter in the last notebook. Then for loss, we're going to use categorical cross entropy. Once again, if you remember from last week, for logistic regression, you might have already used cross entropy loss or log loss, and categorical cross entropy is basically the generalization of that for multiple classes. And then in addition to that, we can also specify some metrics, which might be a little more easy to interpret. So for example, in this case, accuracy might be a little more easy to interpret. So we can also tell what metrics we want to keep track of. But remember, the parameters will only be updated according to the loss function, not according to the metrics. So it's important that the loss function is differentiable because we want to find all those derivatives. But metrics don't necessarily have to be differentiable. Okay, so let's do that. Oh, actually, I forgot. This has timed out. Okay, so I'll have to restart this notebook. Let's quickly run through all of these. Okay, so now we have our model compiled and we are ready to train it. Okay, so before we train it, actually, let's discuss some of these concepts we just glanced over, right? So I said I'll talk about optimizers at least a little bit. So let's actually pick this RMS prop optimizer, and that will give us a sense of what different flavors mean. So first of all, I want to point out that in deep learning, the loss function would be something very complex, right? The landscape of the loss function. it wouldn't have like a global minimum. It would have lots of saddle points and local minima. And what you want to do is you want to converge to some nice minimum. Okay, what does nice mean? That's a different topic, but without going into it, we definitely don't want to get stuck on saddle points, let's say for now, okay? Because that's not even a minima. But a saddle point, of course, has zero gradient, right? So if we use the vanilla flavor of gradient descent, where if you go back to the last notebook, this is our recipe for updating the parameters, right? So each time we are subtracting some small value of the derivative from our parameters. But at saddle points, these derivatives are 0. Okay, so once we hit a saddle point, these derivatives will become 0, and these parameters will stop updating. And one would think perhaps we have hit a minima and that's it. But actually, the model wouldn't perform very well. So how do we avoid that? So one way to avoid this is if we can simulate some concept of momentum into this gradient descent problem. Okay, so if we imagine rolling down a hill, then if you can simulate this physical idea of momentum, then even when we hit some locally flat regions, because of the momentum, the ball will still keep rolling, right? So mathematically, how we do that is basically we can keep track of a running average. And so in that case, we won't just be subtracting the derivative at any given point, but also we'll keep track of historical values of the gradients. And that would help us get out of these locally flat regions and saddle points. So in RMS prop, that's exactly what they're doing. They're keeping track of an exponentially weighted average. So instead of subtracting just the gradient from the parameters, they are dividing by this square root of S factor. And if we look at what this S factor is, it is an exponentially weighted average of previous gradients. Okay, so we compute the gradient at this point, multiply by 1 minus beta, and then add the previous value of S to it, multiplied by beta. So that's just one flavor. You can look into different optimizers. There's also one very popular optimizer called Atom. And sometimes it's just a matter of trying out different optimizers, and some of them can work well in certain settings and others might not. So it's something to try out and empirically see which one is working well for your problem. Okay, also nonlinear activation functions. So we have been using ReLU function so far, which is basically this. So it zeroes out negative values, and then it's just a linear function in the positive domain. So it's if your input is x, it will just output max of 0 and x. Okay, yeah, visually the graph looks like this. Then you're perhaps already familiar with sigmoid function from logistic regression last time. This is also a very popular activation function. Sometimes people would use sigmoid in their intermediate layers. But one problem with sigmoid function is, of course, the gradient is appreciable only for a small range of x values, right? It quickly becomes 0 as you go to the right and left. So which can in turn lead to this vanishing gradient problem. So in fact, with sigmoid, if you do not normalize your inputs so that they're not between -1 and 1, then the gradients would be very close to 0 and your training wouldn't progress. Tanh is another popular nonlinear function. Then there is something called leaky ReLU. So the problem with ReLU is that for the negative values, the gradient is 0. And so if your inputs are consistently negative in a certain layer, then we once again run into this problem of training getting stuck, right? Because your gradients become 0 and then there is no updates. So to deal with that, one can introduce a very small gradient in the negative x-axis. And so that helps with these dying neurons, where the gradient is 0 and the training stops progressing. Lastly, there was this special activation function that we applied in the last layer up here, softmax. And that's given like so. So it's essentially converting the outputs of the last layer to probabilities. So all you do is you exponentiate the values of all of your neurons, and then you divide by the sum of them. In this way, all of the neuron activations lie between 0 and 1, and if you add them all together, they add up to 1. So in a sense, you can interpret them as probability values. And then lastly, the categorical cross entropy is given like so. It's basically the ground truth value times the logarithm of the probability output by the network. And there is a summation across all the classes, right? So in our case, there are 10 classes. We have 10 digits, 0 to 9. So we will, for each digit, we will compute this. And of course, we'll end up computing only for one of the digits, right? So if the ground truth is 6, then y6 will be 1, but the rest will be zeros, right? Up here, and when we one-hot encoded these vectors. Or sorry, y5, because we are 0 indexing. Okay, so we have everything defined, and now it's time to train the neural network. And once again, in Keras, it's just a one-line deal. So we can just call model.fit. We just have to describe what are our inputs, which are the training images, what are our outputs, the training labels. We describe how many epochs we want to train it for. And then there is this last thing called batch size, which we haven't discussed so far. And I think this is a good point to discuss the very first line of this notebook, where we were specifying CUDA visible devices to be 0. So what this is specifying is, it's saying pick the first GPU available on this node, and then we're going to do the rest of the operations on that GPU. So GPU is a graphics processing unit, and this is the hardware side of enabling deep learning. So a lot of these deep learning operations are matrix operations, and GPUs are optimized to do matrix operations, basically. So if you were to run these operations on a CPU, they will be pretty slow. And therefore, in practice, you'll almost always train deep neural networks on GPUs. And so where was I? So the problem with GPU is that it will have a limited amount of memory. So you would only be able to load a certain amount of data onto it. If you load more data, then you would get an out of memory error. So that's why we can't, in most cases, we can't just load all of our input data into the GPU. Instead, we have to go through batches. So let's say we have 10,000 images. In each iteration, we'll just pick 64 of the images, compute the output of the neural network, compute the gradient, update the parameters for those 64 images, and then go to the next 64. And we repeat this until we have gone through all 10,000 images. So once we have gone through all 10,000 images, that's one epoch. And we repeat this 5 times. So in our case, actually, training set had 50,000 images. So we go through batches of 64 until we have run through all 50,000 images. And that's one epoch, excuse me. And yeah, so then we repeat it 5 times. And yep, let's just call model.fit. So you would see this progress bar. It's basically going through the batches, and once it's gone through all of the batches, then that's one epoch. At the end of the epoch, we print out the loss value and then also any of the metrics that we had given. So in our case, we had specified accuracy as one of the metrics. And so what we see is the loss is going down and the accuracy is going up. Okay, so it's looking pretty good. We have reached about 98% accuracy on classifying these 10 digits. But this is the accuracy on the training set. Okay, so one potential problem that can arise is our model can overfit to the training set. And I think you have already gone through this concept of overfitting and underfitting last week, but just to quickly recap, overfitting is when perhaps your model is picking up some idiosyncratic features that are only present in your training set, but are not representative of the data set as a whole. So in that case, it will pick up those idiosyncrasies and fit to those and artificially achieve very high accuracies. But if you were to go and deploy this model or run it on some new data set, then you would see that the accuracy would drastically drop. So to make sure that that doesn't happen, you should always, from the very start, divide your data set into a training set and a test set. So that once you train your model, you can go and check the performance on the test set and make sure you're not overfitting. So we already have the MNIST data set divided in training and test sets given to us. So let's just go and evaluate the model on the test set. So we can evaluate the model very easily by calling model.evaluate on the test images, giving test labels, and it will give you back test loss and test accuracy. So we see that we have about 98% accuracy on the test set, and the loss is also very similar to the training set. So there is no indication of overfitting, which is good. Another thing that can happen is that we are underfitting, meaning we could have kept training for a while and the accuracy would have improved on both training and test sets. So that could also be a potential problem. And so to deal with that is you keep training and keep tracking both training and test accuracies, and only stop when those two accuracies start diverging. So only stop when your training accuracy is still going up, but your test accuracy hits a plateau. Okay, any questions so far? Okay, if not, I just have a couple of words of advice after this stage. So let's say we have trained our model and there is no overfitting, but perhaps let's say the performance is still, it's not something acceptable to you, right? So perhaps the accuracies are too low, or perhaps the model is not behaving very well on a subset of data set. So how to deal with those issues? So first of all, I just want to say, looking at the global accuracy and loss is not enough. You should always go and do a more fine-grained inference on the data set. So one thing you can do is look at the accuracy on each of the classes. So we can do that here. If we go through all of the classes in the test set, we can look at the accuracies for each class. And sometimes if the accuracy is very low on one of the classes, that can be a red flag, right? And that would just point out that you should perhaps go and look at that particular class more carefully. It could be pointing to some noise in the data set. Perhaps the examples for that particular class are corrupted. Perhaps that class is just inherently more difficult to classify. And so just doing a more fine-grained inference gives you some idea about the next steps, like what should be the next steps. So if you see one of the classes have lower accuracy, you can start by looking at the images for that class. You can start collecting more data for that class, or you can at least come up with some kind of explanation for what's happening. Another thing you can do is you can look at examples of your model that it's very confident about. So it could be, these could be very confident correct predictions, but also very confident incorrect predictions, and both of those could be interesting to look at. So here I'm just going to look at random sample of correct and incorrect images. And then incorrect images here. So in the brackets, you see the ground truth value, and then outside the brackets are the predicted values. So you can see the model is performing reasonably well. Some of these examples are kind of hard, but it's getting it right. So this one could be an 8 or a 3, but it's getting it right. And then looking at incorrect examples, we immediately see that, okay, these are qualitatively kind of hard to classify, even for a human. Right, so what is this? It's a ground truth is 8, but really it's very difficult, I would say, even for a human to classify. Whether this is 0 or a 6 is debatable. So looking at, so dividing the data into correct and incorrect classifications and going through that is also something that you should keep in mind and can be helpful. Okay, so in the last 30 minutes, I just quickly want to talk about interpretability studies. So far, these deep neural networks have been sort of black boxes. You know, the way we have been dealing with them, we just arbitrarily stacked a bunch of convolutional layers and fully connected layers, then just applied gradient descent as some kind of magic pill to train them. And even though we are getting reasonably good accuracies, we so far have no idea what's going on inside the model. And this is generally sort of a problem with deep neural networks. That being said, there has been some progress made on this front in the last few years. And there are some popular techniques to begin to try to understand what's happening inside the models. And so I'm just going to discuss a couple of those. So first thing you can do is you can start visualizing some of the very last layers of the model, right? So the last part of the model is a bunch of fully connected layers. And we can go and look at the activation patterns of, let's say, the second last layer and the third last layer and so on. So why do we want to do that? I can give you one example, but there could be multiple reasons why you would want to do this. Let's say, once again, we are classifying images of handwritten digits. And if we look at just the last layer, of course, one of the neurons will have higher probability compared to the rest, just by default of using the softmax activation. So we will always get the input image classified as one of these 9 digits. But let's say in our data, there is some noisy images. So completely out of distribution images, let's say. Instead of handwritten digits, let's say we end up having an image of a cat in our data set. Now, this network was never trained to classify cats. It has never seen cats. But what would happen when we input the image of a cat? Well, one of these neurons is still going to get activated more than the others, and the image of the cat will still get classified as one of these numbers. But if we look at the second last layer, something more interesting can happen. So the second last layer, if you look at the activation patterns there, what you would notice is for when the input image is, let's say, 2, there's a certain activation pattern that comes up in the second last layer, which consequently leads to this neuron getting activated. Similarly, for 1, there's a different pattern that gets activated, which eventually causes this neuron to get activated. So the idea here is, if there was an image of a cat input to the network, then the activation pattern we'll see here will perhaps be different than the ones we see for any of the digits. And so if we keep track of the activation patterns of the second last layer, it might be possible to pick up such anomalies in our data set. So that's just a practical example of why you might want to do this. But it's also good to just confirm what we said, that there are 10 different, let's say, activation patterns for the 10 different digits, which consequently cause these neurons to activate. By the way, this visualization I've taken from 3Blue1 Brown, which is an excellent channel on YouTube. I'd recommend everyone to go check that out. They also have a very nice introduction to deep learning. Okay, so how do we get the activation patterns from the second last layer and visualize them? In Keras, it's very simple. All we have to do is define a new model. So I'll call this the embedding model. Once again, I'm calling this model function. So I have to specify what are the inputs and what are the outputs. Okay. For input, I'm taking the inputs of our original model that we trained on the MNIST data set. So it gets a little confusing here, but remember that this model with small m is the one we trained up here, right? Called model.fit. So this is our trained model with small m. And we can call model.input, and that gives us the input layer of our trained model. So for our new model, we're going to use the same input as our trained model's input. But for the output, we're going to go to the second last layer and grab its output. So you can call this method getLayer on your trained model and specify the name of the layer that you want. If you look at the summary of our trained model, each layer has a name. And so if we see our last layer is called dense1, it has 10 neurons, but the second last layer is just called dense, and it has 64 neurons. So we can call this method .getLayer and specify the name dense on it. And then we can grab its output. And that defines our new model that will give us the activation patterns for the second last layer. So let's just confirm that. So we define this embedding model, and if we call embedding model.summary, then we will see that our very last layer with 10 neurons is gone now. In fact, our last layer is what was previously the second last layer with 64 neurons. So now what we can do is we can pass the test images through the embedding model that will give us the activation patterns for the second last layer. We'll collect them in this variable called activations. And then for the same images, we'll also collect the predictions. So calling small m model.predict will give us the predicted values. So now what we can do is we can visualize these activations and label them by their predicted values and see if we end up seeing any patterns. So let's run that. So first, let's check the shape of the activations. They should be 10,000 by 64 because we have 10,000 images in the test set, and then we have 64 neurons in the second last layer. So now what I'm doing here is I'm just plotting these activations for all 64 neurons on the x-axis. So the x-axis has 64 neurons. And on the y-axis, I'm just combining a bunch of examples for zeros, then for ones, for twos, and so on. So each row here is corresponds to the activation pattern for a single image. So up here, these are activation patterns for images of zeros. These are activation patterns for images of ones, and so on. So you can roughly see that the activation patterns are different for different classes of images, right? So the activation patterns for zeros is slightly different than ones, and this one is slightly different from twos. And so we do see kind of 10 different clusters forming. But this might still be hard to visualize. So another thing we can do is we can use some kind of clustering algorithm to transform these 64-dimensional vectors into 3 or 2 dimensions. So perhaps people are already familiar with PCA, principal component analysis, which we can use to convert them from 64 dimensions to 3 or 2 dimensions. But here we are going to use a different algorithm called tSNE, or t-stochastic neighbors embedding. And you can read up more about that. In the interest of time, I'm just going to skip talking about it in more detail, but it does basically the same thing. it sort of faithfully represents the number of clusters in a lower dimensional space. So for that, what I'm going to do is, first of all, I'm going to write down these activations into a file, and then the corresponding predicted labels also into a different file. So in the vex.tsv file, I'm just writing out all the activations, and then in meta.tsv file, I'm writing out all the labels. So once you run this cell, if you go back here, you would see that you would have two new files, meta.tsv and vex.tsv. So what you need to do is select those two and click download. So that should download those two files to your computer. And then what you need to do is go to this link, projector.tensorflow.org. And so this website has a version of tSNE available. So all you need to do is now upload that same data to this website, and then you can press tSNE, and it will run that algorithm, and you can then visualize the clusters in 2D or 3D. So basically what you have to do is first click load here, and then you'd pick vex.tsv file for vectors and meta.tsv file for the metadata from your local computer. Load it, then you can color the points by the labels. And then finally, you can run tSNE. So this website already has some preloaded data, but you can just ignore that and load your own data for that. And it can take a while to run. So what I've done is already loaded this data and run the tSNE algorithm for 100 iterations. And so after 100 iterations, what you would see is basically more or less 10 different distinct clusters forming in this three-dimensional space. And so I'm labeling all of these clusters by their predicted labels. So all of these red dots correspond to images of ones. These blue dots correspond to zeros, orange to sevens, and so on. So it's basically nice to see that there are, in fact, 10 clusters still forming in the second last layer that correspondingly lead to each of the 10 neurons in the last layer getting activated. And now, if there were anomalies in our data set, then perhaps we would see an 11th cluster forming. So if you do see an 11th cluster forming, that could be an indication that we need to stop and look carefully at our data set. Okay, that's one thing you can do, and I think this has died once again, but it doesn't matter. We can just go through the cells without running them. So that's visualizing the second last layer, but you can also visualize the earlier layers in the network. So the earlier layers are convolutional layers, and those are composed of filters. So what we can do is we can apply those filters to the image and see what are they picking up. Are they picking up some interpretable features? If so, that would be nice. But sometimes we will see that they end up picking features that are not really interpretable to us, but it helps the neural network make the right decisions. So to do that, once again, first of all, because there are a lot of filters in the earlier layers, for example, there are 32 filters in the first layer and then 64 in the second convolutional layer. Just getting the activation patterns for all these filters for 10,000 images can be a lot. So what we're going to do here is first fix a single image, and then just pass that single image through the network and look at the activation patterns for all these filters. That becomes more manageable. So we can go through images one by one and look at the activation patterns. So for this example, I'm just going to pick up one image, happens to be of digit 2, and then I'm going to define my activation model. So once again, the input is my train model's input, but for output, I'm gathering the activation outputs for all the convolutional layers of this model. So I'm passing in layer outputs, which if you look up here, is just a list of outputs for all of the first 8 layers of the model. So we go up here, 1, 2, 3, 4, 5, 6, 7, well, I think I'm just gathering all the outputs of the of all the layers in the model. So this activation model, now once you input an image, it will give you the outputs for all of the layers. And then you can look at them one by one. So we can just pass the image and call activation model.predict on it. And then we will get all of the activations. And then we can see, okay, what is the shape of the first layer of activations? It happens to be 1 by 26 by 26 by 32. 1 because we only passed one image. And if we look at the shape of the first layer, it is 26 by 26 by 32. So that's correct. And then these 32 are different filters. So we can go and look at all the filters one by one. So if you pick, for example, the 6th filter and visualize the output, and we see, okay, this does look something like a vertical edge detector. And if we look at the 12th filter, that ends up looking something like a horizontal edge detector. And so we can go through all of the layers and visualize them. So here, these are the convolutional filters, all of the filters for the first layer. You can see some are vertical and horizontal edge detectors, but a lot of them are hard to interpret what they're doing, right? And then some are dead filters. Perhaps they're dead on this single example, or perhaps they're always dead because of this ReLU activation function. So that's also something good to check by passing in multiple images. And then max pooling layer basically decreases the size of the output in half. And like I said last time, it decreases the size, but retains most of the information. So, and that seems to be true here. And then we apply another convolutional layer. And as we go deeper into the network, these activation pattern, these outputs become like more abstract and hard to interpret. And this is sort of expected because it turns out that neural networks learn these features hierarchically, meaning the first few layers learn simpler features like edges and simple shapes. But as you go deeper into the network, these filters start learning about more complex features and more complex ideas. And so I don't have the quote for that, but I have put a reference to a paper that does actually look at how these deeper layers learn more complex ideas. And specifically, I would point in that paper to look at this figure 2, I think. So here you can see that the first layer is picking up simple features like lines and curves. And then when you go to layer 3, it's picking up more complex geometrical features. And by layer 4 and 5, it's actually picking up ideas about what are dogs and plants perhaps or something. So it has very high level ideas about objects. And of course, as we go to towards the very last layers of the model, they start having an understanding of what a digit is, what a cat is, and so it can classify the entire image. Okay, so that's one thing we can do, visualize the filters. Another thing, interesting technique is called GradCAM. And the idea here is, well, first you fix one of the late layers in the model, let's say this one. So actually you have to pick a convolutional layer, not the fully connected one. So you can pick the very last convolutional layer. And then you can ask the question, okay, if I change the value of one of these filters or one of the neurons of the filter by a little bit, how much does my output change? Okay. So by doing this exercise, you can find out how sensitive your output is to each of these neurons in your last convolutional layer. Once you do that, you can gather all the most important neurons together and then map them back and see what areas of the image these neurons were looking at. Okay, so here if we go back and look at the receptive field of, let's say, this neuron, perhaps it was looking at this patch of the input image. Okay, so this way we can find out for a certain classification what areas of the input image were important. Okay. So the whole procedure is pick an image, make the prediction, then take the gradient of the prediction with respect to neurons in the last convolutional layer. That basically gives you an idea of which neurons are important for this prediction, and then map back to the input image those neurons' receptive field to see what areas of the image the output is most sensitive to. So in this way, you can find out, okay, when my neural network said this was 4, what areas of the image it was actually paying attention to. So you can begin to sort of understand more how the neural network is making predictions with this technique. So once again, I've listed the paper for you to go in more detail, but I've also pasted the code here, taken from the Keras website, just to show that it's very easy to implement. And so if you run this code, then we can actually create these maps. So here, I'm just picking one image, happens to be a 1. Then I pick the last convolutional there. And then I go through this whole procedure that I described, which are defined in these 2 definitions here. So first, you find the gradient of your outputs with respect to this layer, and then you map back the receptive field of this layer onto the input image. So that gives you a mask. Basically, then you have to resize the mask to match the dimensions of your input image, and then you can superimpose those 2 together to see what areas of the image the network was paying attention to when it made this classification. So for this one, when the network predicted that this was actually a 1, it was paying attention to this region, the bright region here. So that just reaffirms that it was roughly looking at the right region in the input image. And so we can do this for a bunch of different images. And we can see that roughly the neural network is paying attention to the right patches of the input image when making classifications. But since our neural network is very small and this is the toy data set, these visualizations are not that great. Once you move to slightly larger neural networks and train on millions of images, then GradCAM sort of becomes very powerful and these visualizations actually become more crisp. So if you go and look at the GradCAM paper, they show some examples. So here they're doing multi-class classification. They're given an input image, they're classifying multiple objects in it. And so then they ask the question, when the model predicted this was a cat, what parts of the image the network was paying attention to? And it looks like it was paying attention to the right area of the image. And similarly, when the model predicted there's a dog in the image, it's paying attention to the right part of the image. So this can be powerful because if the network makes an incorrect classification, then you can apply GradCAM to see sort of why is it making a misclassification. I think they have an interesting example down here. So where they're showing, because of some bias in the data set, how the model can also be biased. So they input images of a nurse and a doctor, but in both cases, the model is predicting nurse. And when they did GradCAM, there turns out the model is paying attention to the face rather than more expressive features corresponding to a nurse or a doctor. So this is a big red flag. It shows perhaps there are problems in your data set and how they're labeled. So to fix that, then you have an action plan, basically. And after they fix it, then the model ends up paying attention to the correct features. So a stethoscope is perhaps more indicative of a doctor, and a blue dress is more indicative of a nurse. So this can be a powerful tool to help deal with incorrect examples as well. Anyway, so I think we are out of time. In the last notebook, you can go through it in your own time, but all I've done there is just go through a few more advanced examples using color images and then introducing the idea of data generators. So when you have to read a lot of images on disk, you can't just load them all into an array. So then you have to make use of data generators. Then also I have a couple of examples on how to deal with overfitting. So that's all, but I hope that you can go through that notebook on your own time, since we are almost out of time here. So in the last couple of minutes, I will take any questions.
Thank you, Asad. It was very nicely done. So just a reminder for all attendees, you know that you can continue the conversation in Slack. And you also have access to a channel that is labeled feedback. So please let us know what you think of these training sessions, things that you have enjoyed the most, things that we can do better. Feel free to share your feedback. It is most welcome. And we have a couple of minutes for additional questions. Feel free to ask any questions to Asad at the moment.
Hi, Asad.
Hi.
I had a quick question. Do you know if there's any sort of interpretability software for things that aren't image classification? So if you're doing like continuous variable regressions, but you're still using a deep neural network?
As far as I know, it kind of depends on what architecture you're using. So when you're dealing with time series data sets, some of the interpretability techniques will be dictated by the model architecture. So if you have heard of attention-based models, for example, those are sort of easy to interpret, at least at first. Mm-hmm. But as like a global or a general purpose interpretability software, I'm not really aware of for deep learning.
Okay, thank you.
Yeah.
I hope that you take the time to go through these notebooks again. If you have any questions, feel free to reach out to us through Slack, and please send us your feedback and suggestions about what other topics you would like to see in these training sessions in the future.
I would like to just remind that next week is supercomputing, so we won't be having a session next week. The week after is Thanksgiving. So I wish everyone a very happy Thanksgiving, and we'll be meeting next on December 2nd.